measurement theory is emphasized that a measurement must be descriptive with respect to what we are trying to measure. It also must be selective in that our measurement only provides information on what we want to measure, and it must be objective, meaning that the measure is independent of the observer. The conditions of the measurement must be controlled so that the data can be interpreted and the underlying relationships between the inputs and the outputs understood. For example, this could mean that a certain variable for maybe an operator could be varied to understand the effect that the particular operator has, or that the operator be the same for all measurements in order to remove the influence of that variable. Next, the sampling plan must be constructed such that the sample is sufficient to establish the effect of any input changes and to give an acceptable level of certainty about this effect. The variability of the measured outputs will affect the sampling plan, so we need to look at sources of measurement error, which we discussed when we talked earlier about the measurement system analysis. So to design our sampling plan, we take the prioritized input process parameters and we specify them exactly, as well as the outputs that are to be measured. The goal of the measurement needs to be documented, along with the sample size and frequency and the data type to be measured. So very carefully documented and clear for everyone involved. The necessity to actually run an MSI must be also determined, and that was also covered before. Very important that the measurement error is not too high. And finally, you need to develop a sampling plan. What should be tested with which methods? And in the analyze phase, which is covered in the next course in these series, you also would establish the hypotheses to be tested. These should also be clearly identified and documented. First, the homogeneity of the data is critical in order to control the influence of unwanted factors. And this is one of the important principles of research. Ceteris paribus, all things equal, or under the same conditions. This is critical because any unintended or uncontrolled conditions could distort or even hide the effect that is under test. An example could be, for example, that samples are taken inadvertently at different temperatures, or different samples are taken by different operators who measure very differently. The conditions for taking samples should be identical and as close to constant as possible. These variables are often called blocking variables, background variables that cause unintended variation. And important considerations when you're thinking about blocking variables are, for example, who? Do you have different operators? Do you have different shifts? Or, for example, what? Is there particular suppliers, particular products that you're measuring that might block the results of the experiment? When? Time of day? Or the day, for example? Things with seasonality could be affected by when. How? With a procedure that must be identical in order not to have any blocking of your results. And where could also be if you're taking your sample only from a particular region or from a particular production line, but you're interested in the result for over the entire factory over different regions. So all of these need to be thought about and considered when designing your sampling plan to ensure data homogeneity. Now, as we just said, the blocking means to spread, if you want to spread the variables to avoid blocking, you mean to spread the variables across the experiment to neutralize their effect. But there's another, we'll look at this a little bit later in the design of experiments, this is another opportunity. You could actually be interested in these variables. For example, in a medical study, you might want to include how age or gender affects your results. So you'd actually decide as part of your study to include each of these variables. Maybe I should write, avoid the blocking. You want to spread the variables all across the experiment, but one option would be to include those. And then you have yet another corner of your experiment that you could look at. Now, sample size, this is always the big question. This is a topic unto itself, and I've decided here we're not going to talk too much about the math. We're just going to list a few things that you need to consider. So as you already should expect, there's a relationship between, for example, the strength of an effect. So if the effect is weak, then you need to have a larger sample size in order to see the effect. Variability of the measurement is also important. If you have a very high variability in your measurement for whatever reason, then the larger the sample size should be in order to see the effect that you're looking for. And finally, as we come also later in the course, the higher the confidence that you need in your results, the larger the sample size should be. So if you want to be very sure, you should take a larger sample size. And of course, this is going to be limited then by the time you have. It's also impacted if you have a destructive test on an expensive part. You're probably not going to want to have a very large sample size. And also the time. If this test is taking your production time, it could be reducing your throughput. So the question then always comes up, what is the right sample size? Well, this depends on these factors. It depends on what type of data you're collecting, whether it's discrete or continuous. And hopefully we'll get some good information on this discussion board on this point. In my sampling days in semiconductor production, we had 5 different points on the semiconductor wafer that we took, trying to take the different points of the wafer, and then we had lot sizes of 25 wafers, and we took 5 different wafers from the lot. So it can be very, very specific depending on what you're working on. So what I decided here to put in was, if you want to get started, try a sample of at least 30 to be a good starting point. So I'm going to write this down at the risk of being yelled at, just as a starting point. As we'll see in control, sample sizes of much smaller, like 4 and 5. They also allow us to use the central limit theorem and generally keep things then more manageable for in volume production. So we'll discuss this more in the second course in this series. Now, types of sampling. First of all, we have the idea of sampling from a population, where the sample is taken from a fixed group. We have no time element here. So could be an example, you're looking at all the production, or production quantity, or all the items in a warehouse, for example. We're a little more interested in this course in the process samples. These are samples taken from a flow of items where we do have a time element. So this could be, for example, the products that are shipped every day or every week. This could be the complaints coming in every week. The new customers, again, per month, something, you have a flow of items. Most of the statistical training does focus on samples from populations. But in quality, as we said, we're looking at business processes. So process data gives us more information, for example, trends, than population data. And again, as we'll see also in control, this is the foundation for process monitoring. Random sampling is best when considering populations versus process. 2 commonly used random sampling techniques are simple random sampling and stratified random sampling. In simple random sampling, here, the sample is chosen from the entire population such that each element in the population has an equal chance of being included. In stratified random sampling, on the other hand, and this is the example with the blocking elements, you have different criteria. Different, for example, we had age, or we had maybe different regions or different production line. The population is first divided into these different strata. And then you use simple random sampling is done within each strata. So from A, strata A, like region A, production line A, then you do random sampling. And this provides better, so you take always a fixed or proportionate amount will be randomly selected from each strata. And this provides better precision, meaning less variability in the estimates for a given sample size given to the simple random sampling tends to. If you have process or population or process, you can also use systematic sampling. It makes more sense when you're measuring a process. What this means is every nth element will be measured. So you have this idea of time. So as the process continues, you measure an element, or you measure an element, and then it continues along, you measure the next nth element. You can also have subgroups, so where you measure n units measured in regular time intervals. So here what we're trying to show is you have every half an hour, 6, 6:30, 7, 7:30, you take a subgroup at the end of every half an hour. And this is also very useful when you're measuring process and you're looking for trends. The only risk here, though, is if there's a pattern in the process that follows the same time sequence, then the sampling will actually hide this pattern. Or if you have some kind of pattern in the process that might distort then your pattern just because the sampling is also picking up that pattern, that could be one of your risks.